We now turn our attention to planetary and satellite motion. The orbit of a planet around the Sun or the Moon around the Earth, as shown by Kepler, is an ellipse. But for our purposes for this course, it can be assumed to be circular for simplicity. This statement here, that the gravitational force provides the centripetal force for the satellite, is very important. You should write this in your answers if you want to use the equation gmm over r squared equals to mr omega squared. So what this equation means is that the resultant force on the moon, in this case, that's the gravitational force, is the only force acting on the moon in this case, gmm over r squared. It provides the centripetal force that is needed to keep the moon in a circular motion. And this resultant force, according to Newton's second law, is just equals to ma, right, where a is v squared over r. So if we substitute in the period of the moon, right, or planets, in the case of planets orbiting the sun, we find a very useful relationship, t squared proportional to r cubed. This is actually Kepler's third law. And so by doing this, we are actually showing that Newton's law of gravitation leads to Kepler's third law. So here we have two useful results, that the period is proportional to the square root of r cubed, and the orbital speed is proportional to the square root of 1 over r. Capital M here is the mass of the sun, or in the case of the lunar system, it's the mass of the earth. Okay, so both the period and the orbital speed does not depend on the object, the mass of the object that is orbiting. So to illustrate this, we can look at some numbers, right? So this is the planets in our solar system. The orbital period increases as you move away from the sun, right? From Mercury, Venus, Earth, Mars, and so on, right? It increases all the way to Pluto. But the orbital velocity decreases as you move away from the sun. Okay, so we can also answer one of the question that I hinted at the very first lecture. Why does an astronaut in a satellite orbiting the Earth experience weightlessness? This is what we commonly see in videos of astronauts floating around in spaceships, and also when we read books or watch the movies about space travel, right? So why does an astronaut experience weightlessness? Although remember that when we calculated the G in the International Space Station, it is about 8.8 meter per second squared, right? So imagine that this is the International Space Station. The astronaut in the space station actually experiences the gravitational field strength that is quite close to the gravitational field strength on Earth, right? It's 8.8 versus 9.8. Okay, not too far away from the Earth. But yet, if you watch videos of this astronaut, you will see that this astronaut is floating in the International Space Station. So why is it so? Okay, the reason is, if you were to analyze the forces on the astronaut, okay, given by these two arrows, the red arrow and the green arrow, we find that the gravitational force, okay, in this case is mg, and g is 8.8 meter per second squared. This gravitational force fully provides the centripetal force required for circular motion. This astronaut is in the spaceship, and the spaceship is in circular motion orbiting around the planet, and the astronaut has to be orbiting the planet as well, okay, for him to remain in the spaceship. So Fg fully provides the centripetal force for circular motion. As such, the normal contact force is zero. So what the astronaut feels is that there is no contact force between himself and the spaceship, so he will experience weightlessness. Okay. Next, we will talk about the energy considerations. We have already found the period and the velocity. What about the energy of a satellite that's orbiting Earth? Okay, so we can use the Newton's law of gravitation, right? That's the force, gravitational force provides the centripetal force equals to ma, right? And since kinetic energy is half mv squared, we can express the kinetic energy of this satellite as gmm over 2r. And we already know the expression for the potential energy. We can combine these two terms to get the total energy of the satellite, which is minus gmm over 2r. Right? Notice that it is negative. Okay, the total energy of a satellite that is orbiting Earth is negative. So this slide shows you the summary of the three expression: kinetic energy, potential energy, and total energy. Why is the total energy negative, and what does it mean? Okay, the total energy is negative because the potential energy is more negative than the kinetic energy, right? The magnitude of the potential energy is bigger than the kinetic energy. And when the total energy is negative, that means that the satellite is in a bound orbit, right? That means that there's no way for the satellite to escape to infinity, right? Because we know that at infinity, potential energy is zero, right? And kinetic energy cannot be smaller than zero, right? So at infinity, the total energy of a satellite has to be larger than zero. So if you are in a bounded orbit, the total energy is less than zero, and hence it cannot escape from the gravitational pull of the planet. So this is similar to what an electron experience when the electron is moving around a nucleus. Okay, you can actually learn more about this in the later topic, electrostatics. All right. So in order for you to you to allow the satellite to escape, you need to do some external work on the satellite, okay, to move it away from the Earth. Graphically, we have these few graphs that can show you what is the relationship between energy and the distance from the surface of the Earth, right? Kinetic energy is always positive, right? And potential energy is always negative. And since the magnitude of the potential energy is always bigger than the KE in a circular orbit, that the sum is always negative. Okay, for a very long period of time, the moon is the most convenient satellite for scientists to observe, right? Because we have no technology to send artificial satellite into space. So when gravitation as a topic was developed, scientists can only study the orbits of planets around the sun and the moon around the Earth. Okay, but after the technological breakthrough that allows us to send satellite into space, we can actually now consider many different types of satellites. One of these type of satellite is quite interesting. It's known as the geostationary satellite. Okay, so what do we mean by geostationary? That means that this satellite, when it orbits the Earth, always remains above the same location on the Earth. Right? You can pick up a ball and two balls, in fact, and try to visualize this situation. You'll find that in order for a geostationary satellite to be always above the same spot on Earth, it has to fulfill these few features. First is that this satellite has to be in an equatorial orbit. Otherwise, there's no way for this satellite to always remain above the same point. Okay, it has to have the same period as the Earth, so as the Earth rotates, the satellite moves above the same spot. It has to move in the same direction of rotation as the Earth, and as a result, they will appear to be stationary above the equator. It can only be above the equator, alright? It cannot be at any other latitude. Okay, so we can do some mathematical analysis on these kind of satellite to find where this geostationary satellite has to be. In fact, there is only one possible distance away from the center of the Earth that you can place these geostationary satellite. Okay, so we'll use the gravitational force provides the centripetal force. Okay, so gm/r squared equals to mr omega squared. Put in the values for period. Right, for geostationary satellite, we want the period to be 24 hours. Alright, because we know that the Earth rotates about its own axis once in 24 hours. Okay, so the period here is just the period of rotation of the Earth. And we find that the geostationary satellite has to be in orbit at a distance of 4.2 times 10 to the power of 7 meters away from the center of the Earth. Okay, one example of the geostationary satellite is the European Geostationary Navigation Overlay Service. So this service complements the GPS system, as in it provides very good positioning for objects on the surface of the Earth. Alright, so besides the equatorial orbits, there are different kinds of orbits. One other form is the polar orbit, whereby the satellite goes from south to north. Okay, orbits Earth from the south to the north and back to the south. Geostationary satellite has to go from the west to the east, okay, east to the west. Okay, and there are other satellites that fall in between. Okay, so it need not be at right angles. It can be at different angles to the poles. Okay, and for more complex satellite systems like the GPS or the Galileo that was launched by the European countries, and even the more recent Beidou that is launched by China. These are more complex global positioning satellites that consist of not just one satellite but 20 to 30 satellites. Okay, so these satellites will orbit Earth in different angles so that they will offer very good positioning of objects on the surface of the Earth. So from the discovery of gravity to the formulation of Newton's law of gravity, we have came a long way, and all these scientific discoveries have led to what we now in everyday life take for granted, right? The services like GPS, they all rely on a good grasp of nature, of how to launch satellites into orbits, and stuff that orbits around the Earth, but we can't really see, but we are now enjoying the fruits of the scientific discoveries.